Okay, so we're close to being able to prove the mean value theorem already. What we're going to prove next is called Rolle's theorem, which is sort of a special case of the mean value theorem when the mean value in question happens to be 0. And it turns out that it's easy to derive the general mean value theorem from Rolle's theorem, basically. So let's state and prove Rolle's theorem. So let's see. Right. So this is theorem 29.2, which is Rolle's theorem. Let f be continuous on the closed interval AB and differentiable on the open interval AB. And suppose f of A equals f of B. So then, then there exists an x in AB such that f prime of x equals 0. Okay? So, the picture here is kind of like, I mean, basically, if you think about it this way, if you think about it in terms of like extrema, this is just saying that f achieves some local extremum somewhere. And actually, I mean, since we're assuming that it's differentiable on the entire interval, and it's continuous on the it's differentiable on the entire open interval, and it's continuous on the entire closed interval, we know that like it's if it's continuous on the closed interval, it achieves a global max and a global min somewhere, right? I mean, weakly at least, right? So they might not be strict global max and global min, but it achieves some global max and global min somewhere. So at those points, unless they're the endpoints, it's automatic that f prime would have to be 0, right? So it's kind of, it actually almost seems obvious in a way, right? Pictorially, assuming f isn't constant, then it's just like, so we have, here's like A, here's B. So the values are equal, at least theoretically. It's a little bit off. So then, right, say, f, I don't know, who knows what it's doing. But as you can see here, there are actually multiple places where f prime is 0, right? So Rolle's theorem is just saying that there is at least one place, right? And it makes sense that it couldn't be like, it just couldn't be like strictly increasing or strictly decreasing the entire time. It has to, go back and forth. If it varies at all, it has to go up and down. And so it has to like, max out or bottom out at different points. So the proof is basically just that. Since f is continuous on AB, it achieves global max and min on AB. Suppose both extrema are at the endpoints. Since f of A equals f of B, this means that the max of, the max of f of AB to use our convenient notation, is the min of, of f of AB, which would equal either, f of A or f of B. They're the same thing. So f is constant, right? So clearly, if f is constant on AB, then f prime equals 0 on AB. So that proves that case, right? Because then then f prime is just 0 on the entire interval. So any value in AB, in the open interval AB, will suffice, right? On the other hand, on the other hand, suppose f achieves, a max or min at x naught in AB, then 29.1, theorem 29.1 tells us that f prime of x naught equals 0, right? So that's the theorem, and yeah, I think it's a short video. I think that's it for this video. Yeah. In the next video, we'll generalize this to the mean value theorem.